So my name is David Berman. I'm a surgical pathologist and I run a research lab. I'm also the head of the Department of Pathology and Molecular Medicine at Queen's University in Kingston, Ontario, Canada. I've been working with Visiopharm, mostly with Reagan Barrett and Dan Witkowski for several years, maybe since 2021 or so. And our project is focused on turning bladder cancer grading into an objective algorithm. Right now, it's more of a judgment, and so there's a lot of variability from pathologist to pathologist in how grading is done, and I'll run you through some slides that I often show to explain this project. These days, pathologists split the grading of early bladder cancer into low grade and high grade. And if you have a low-grade cancer, the patient will be managed with infrequent surveillance. And surveillance means that a camera is inserted through the urethra to look around in the bladder and see if there are any new tumors there. So that's an uncomfortable, expensive, and inconvenient experience to go through for patients, and it costs health systems quite a lot of money, making bladder cancer the most, or one of the most expensive cancers to have. And if the cancer is high grade, the patient is offered more frequent surveillance plus intensive immunotherapy that is squirted into the bladder. And the difference between low grade and high grade is illustrated here. And so the low-grade tumors have relatively uniform-looking nuclei. You can see most of these are oval, and they're pretty much in this. They're very similar in size and shape, and most of them are even oriented in such a way that it almost looks like you took a comb and combed the nuclei from, let's say, the bottom of the screen towards the top. So it's a well-organized tissue. The cells respect each other's space and align well with each other, much the same way that they would in the benign tissue that this cancer arises in, which is called the urothelium. And on the right, you see a high-grade cancer where you don't get the sense that every nucleus is oval. They seem to be oriented in all different directions, and you'll notice that some are larger than others, and then there are this one and this one here. Some of them are undergoing mitosis, so they look kind of like eyelashes or spider webs, and those indicate that there's rapid proliferation. So like many studies before us, we found that the best possible agreement you can get from very expert pathologists like me, who've been specializing only in urologic pathology for 20 years or more, is about 80%. And so we had experts at 3 different academic centers look at our cases, and we found that the same cancer, depending on which pathologist looks at it, would get treated differently about 1/3 of the time. And that's about the best we can do, because it's all a bit of a judgment call. We have a large number of features, and I'm not going to go through all of them, but I just wanted to show you that this is a complex group of features that describe the size, shape, and orientation of the cells in bladder cancer and decide whether they're low grade or high grade. And this is kind of a judgment call. There's no measurements or numerical values in any of this. So for example, low grade may have occasional mitoses, but they're usually frequent in high grade. Well, what does occasional and frequent mean? And what's the difference? And where do we draw a threshold? So that's the work we addressed, and we published this work in collaboration. You'll notice Reagan Baird and Dan Winkowski from Visiopharm are part of this project. And this was led by Ava Slotman, who was then a graduate student in the lab. And it's the biggest study of nuclear measurements as a part of grade. We measured more than 3 million nuclei from 371 cases. That's 641 images. And using Visiopharm, we're able to measure every single nucleus in every case, every cancer nucleus. And that included an automated app that we trained to distinguish the cancer tissue from the benign tissue. So this kind of pink area that's outlined in a gray dotted line on the upper right, that's benign tissue. And the nuclei in there are not counted in the calculations. And then outside that, every single cancer nucleus is circled in white unless it's undergoing mitotic duplication or proliferation, and those are circled in green. So we get this enormous data table that we can then put into complex analysis and algorithms and ask, what is the difference between low grade and high grade? So we did this measuring a wide variety of features, and Visiopharm gave us quite a lot of relevant features to look at. I'm not going to go into this slide in detail, just to say that there were many different attributes that we measured for each nucleus. And we found that the most informative single variables that distinguish between low grade and high grade were the variation in nuclear size, in this case area, and the mitotic counts. And each one of those was about 80% accurate in distinguishing between low grade and high grade. And then we could make more sophisticated algorithms that added a bit more accuracy, things like random forest and decision trees and logistic regression. So we think we've redefined and simplified grading to measurable features, and we actually were able to externally validate one of those algorithms called the random forest in another cohort. And using these features, we can actually make grading better. So this is unpublished work with Catherine Lindahl showing that we can make prognostic scores by reprioritizing those features I've shown you. And we're able to, these are curves that show the time to recurrence. So when a cancer is removed, how long does it take for a second cancer to occur? And on the left is regular pathologist grading on the entire case. And you see a bit of a difference between low grade and high grade, but because these clouds kind of overlap, it's not a very dramatic difference. It has it is statistically significant. But on the right, you see this reprioritized grading algorithm using numerical cutoffs, and we get a much lower p-value and much more distance between these curves. So especially the bottom curve recurs faster than high grade, and the top curve recurs slower. So this could really guide treatment, where these patients with low prognostic scores would be treated with less frequent surveillance, less frequent cystoscopy, would not need the immunotherapy, and these higher risk patients would get all of the intensive surveillance and treatment that they need. So that's a summary of what we did with Visiopharm and what we're working on. Most of this work was done on small image samples. We're now working through an algorithm for whole slide images, and that's going well.
Great. So the second question is, what challenges or limitations in your research led you to consider using AI solutions like Visiopharm software?
Well, previous studies had done either manual measurements of each nucleus, which would mean that we'd only be able to do maybe 100 per case instead of thousands, and we'd may be able to get 1,000 nuclei very slowly instead of millions of nuclei. And so this this higher throughput allows us to do much more sophisticated analyses. And when you also just the number of features, like I don't think we could have manually assessed and measured every single one of those features that I showed you.
Yeah, right. And how has the use of Visiopharm software improved the quality of and accuracy of your research outcomes?
I think that's the same answer, pretty much.
Okay, efficiency. Cool. Then let's see the next one. In what ways did Visiopharm prove to be the only viable solution for your research needs compared to other tools or methods you
When we were
considered?
choosing tools and pathways, or tools and when we were choosing image analysis software, we found that Visiopharm had a lot, it was able to produce a lot richer data set, meaning there were a lot more features already built into it. And it was a lot easier to sequence a number of different feature detectors, one after the other, in a pipeline, so to speak. There were also some pricing considerations where some of the other commercial vendors would charge you for each of those types of analyzers or software, whereas Visiopharm gave us access to pretty much the entire package. So those were some of the reasons. And then we had really fantastic customer support. I mean, we felt like they were collaborators. They were collaborators in the work. And that was very important to us and made the project go much better, and still is to this day. I mean, I guess one other thing that was a consideration was that we wanted to work with a group that could help us get this classifier onto a clinical desktop at some point. And we knew that Visiopharm had connections that could do that. So we don't want it to live forever only in the research environment, but we're working towards getting it into clinical operation, because we think this kind of approach can very much improve patient management.
Okay, and what is like stopping you now from moving into the clinical operation, as you said?
I'm sorry, repeat the question.
Yeah, so what are the next steps for you to move from research to clinical?
So the major thing we're doing now is moving this again from small image samples that are about 1 millimeter in diameter to whole slides, because pathologists diagnose bladder cancer and every kind of thing they diagnose on whole slides, not on small image samples. and that will actually give us some more power to look at heterogeneity in these features and see, you know, is there a certain area that has to be high grade, let's say, to drive a bad prognosis. That's something that other investigators have done qualitatively, but there's a huge opportunity to do it quantitatively using these tools. And then, of course, there's always a need for external validation cohorts, and we have a number of collaborators that we're working with to make that happen.
Mm-hmm. Cool.
I guess another thing that's worth commenting on is that there much of AI use in pathology uses AI as sort of a black box where the image analysis program just matches the image to a previous set of images and tries to emulate expert opinion. And we're trying to do something, I think, a lot more impactful, which is to make pathology work better than it did before, not just to make bad pathologists work, as better at what they do more like a good pathologist. We're trying to make good pathologists do better work. And there is no opportunity in regular everyday practice to look and match what grading practices with actual patient outcomes. You'd have to go back, years later and see what happened to that patient, go back to the grading and alter what you're doing, and you'd have to have measurements to do that. And this research provides us with a new opportunity to do that kind of work in a way that is vastly accelerated through the use of AI and this sophisticated computational technology.
Yeah. A lot of pathologists are still afraid of being replaced by AI, right? I think there's some resistance. Yeah.
Yeah, and I've heard even very sophisticated pathologists say that. I wonder though, do we really want to trust a program to tell us, to help us make a decision? Well, just to make the decision without an expert, without a human expert, that's going to tell you that you need some very invasive and life-altering surgery or chemotherapy or immunotherapy without any oversight from an expert. I don't see that happening anytime soon.
Yeah.
We don't even have driverless planes, much less, not carrying passengers anyway. I don't see it.
Yeah, I think we are very far from it. I agree. Yeah.
All right. Well, I'm glad I could be of assistance, and
Yes.